Linear regression predicts continuous variables, like age versus income, but real-world questions often have binary outcomes, 1 or 0. Here, a straight line fails, predicting impossible values below 0 or above 100. To respect these boundaries, researchers use logistic regression. Abandoning the linear slope, logistic regression measures relationships using a new metric, the odds ratio. Conceptually, an odds ratio quantifies how a specific characteristic increases or decreases the odds of an event occurring relative to a baseline. Predicting binary choices requires a different statistical engine. This capacity to handle absolute outcomes makes logistic regression essential for behavioral and public health research. In 2009, the United States faced the H1N1 pandemic, its first major influenza crisis in 40 years. The virus resulted in over 60 million cases, creating an urgent need to distribute a separately administered pandemic vaccine. Data showed that Hispanic populations were at a higher risk for H1N1 complications, yet their vaccination rates remained remarkably low compared to non-Hispanic whites. To understand the drivers of this disparity, researcher Andrew Berger conducted a study in 2018 to differentiate outcomes within the Hispanic community. Berger utilized fundamental cause theory to hypothesize that the barriers for U.S.-born Hispanics would differ significantly from those facing foreign-born Hispanics. He employed a series of nested regression models to test this, and notably, he did so while maintaining an objectively magnificent mustache. We will use his data to reverse engineer logistic regression, decode his odds ratios, and see how he uncovered the hidden mechanisms of vaccination uptake. Mastering abstract statistics is only the beginning. The math earns its keep when we use it to pinpoint why specific groups are left behind during a national health crisis. We'll start with the unadjusted findings from Berger's research, looking specifically at the initial model. Logistic regression requires a reference group. To compare categories, we have to pick one group to serve as the fixed baseline. In this model, non-Hispanic whites are the reference group, which means their odds are fixed at exactly 1.00. Now, look at the finding for foreign-born Hispanics. Their odds ratio in this first model is 0.77. On the odds ratio scale, a value of 1.00 means equal odds. Anything higher than 1 means greater odds, and anything lower than 1 means lower odds relative to our baseline. Since 0.77 is less than 1.00, we know the odds of a foreign-born Hispanic getting vaccinated are lower than the white reference group. However, we must address the most common professional error in data science. Odds ratios are not probabilities. Describing this 0.77 value by saying the population is 23% less likely to get vaccinated is a mathematical mistake. It misrepresents the regression's logic. The correct phrasing is, the odds of vaccination for foreign-born Hispanics are 0.77 times the odds of the white reference group. Precision in this language is vital. Confusing odds with probability miscalculates the magnitude of real-world risks, which can lead to flawed policy decisions. A single regression is often just a starting point. Researchers use nested models to sequentially add new control variables, tracking how the initial odds ratios shift. When we reveal Berger's final model, we see a dramatic shift. The original 0.77 odds ratio has transformed. The mathematical disadvantage for foreign-born Hispanics has inverted. In Model 3, it is now a slight advantage at 1.17. This happened because Berger controlled for flexible resources, factors like education and household income. The single most powerful variable added was healthcare coverage. It carries a massive odds ratio of 1.91. This illustrates the mechanism of mediation. Access to healthcare coverage explains the initial negative odds associated with nativity. When the model mathematically accounts for resource disparities, the disadvantage associated with being foreign-born disappears. This is the primary utility of logistic regression. It allows us to mathematically distinguish identity from socioeconomic circumstance. This methodology isolates structural causes from demographic correlations. The low uptake among foreign-born Hispanics reflected a system-level lack of healthcare coverage, not a behavioral trait of the population. Researchers often visualize these shifts into charts to make the complex data actionable for public health officials. This chart is Figure 1 from Berger's study, which visualizes the regression model for foreign-born Hispanics. This bar shows that healthcare coverage is the most significant predictor on the chart, with an odds ratio of 1.53. In practical terms, this tells us that among foreign-born Hispanics, the odds of vaccination for those with coverage are 53% higher than the odds for those without. The horizontal black lines are error bars, representing the confidence interval. This is the visual test for statistical significance. Because the entire interval for healthcare coverage stays to the right of the 1.00 line and never crosses it, the finding is statistically significant at the p less than 0.05 level. Compare that to the bottom bar for region of birth. Its odds ratio is 1.01, but the error bar crosses the 1.00 baseline. This visual tells us the result is not statistically significant. If an interval crosses the baseline, the variable did not definitively change the odds in our population. When we step back from the individual variables, the broader goal of logistic regression becomes clear. This process transforms raw binary data into a rigorous test of sociological theory. It is a powerful mathematical way to pressure test our preconceived assumptions about why people make specific choices. By comparing odds ratios through nested models, we can move past surface-level observations and identify structural causation. Berger's application of this math pinpointed the exact barrier, healthcare access, that prevented a vulnerable population from receiving medical care. For any student of public health, knowing how to interpret these outputs is the first step in drafting effective policy. Competency in logistic regression provides the tools to identify the hidden structural mechanisms that drive human behavior. It is the difference between guessing why a policy fails and knowing exactly where the barriers are.